Here we have a homework problem dealing with the second law and really dealing with the definition of temperature on the absolute Kelvin scale. So what we have here is a power cycle and a heat pump, and we have a source of heat transfer over here, and we have a dwelling, and we have this outdoors, which is a little cooler, and they all have different temperatures where the temperature of the source is higher than that of the dwelling, and the dwelling is hotter than the outdoors. And our goal in this problem is to figure out this ratio, the ratio of the net heat transfer into the dwelling divided by the heat transfer coming from the original source. And we want that as a function of these three temperatures. So if you remember your definition of the absolute thermodynamic temperature, it's the ratio of heat transfer from a reversible power cycle. But you're not allowed to just take these temperatures and replace them. You can't just take TD for the dwelling and put it in for Q1, Q2, and QS. It has to relate to an actual cycle. So the first thing I'm going to do is this energy balance, which they already drew this system out around both the heat pump and the power cycle. So if you do that, you'll get an energy balance with Q1, Q2, Q0, and Q source, or QS. So let's go ahead and do that. If we do that, we have Q source coming in. We also have Q from the outdoors coming in. That has to equal what's leaving the system, which is Q1 plus Q2. Now what we're looking for is Q1 plus Q2 divided by Q from the source. So we have Q1 plus Q2 on this side. All we have to do is divide by QS on both sides. So if you do that, you get something. If I divide by QS over here, you have this divided by QS, this divided by QS, and that is equal to 1 plus Q naught over QS. So here's what we're looking for, and here's what we need to replace. We need to replace this ratio, Q naught over QS, with a different set of things dealing with these temperatures. So notice that Q0 is here related to the heat pump, and QS is related to this power cycle. So this is not equal to T naught divided by TS. That is not the case. We need to do a little bit of rearranging. So since we need heat transfer items related to the same cycle, we need to somehow divide each of these by their other corresponding heat transfers. So for Q naught, it would be this Q2, and for QS, it would be Q1. So what I'm going to do is I'm going to actually write the energy balances for the power cycle and the heat pump separately. So let me go ahead and write that. For the power cycle, you have, I'm going to call it just work between the two. That is equal to the source minus Q1. Let me just double check that that's correct. Yes, source minus Q1. And for the heat pump, we have the work is equal to Q2 minus Q0. So that should be straightforward enough. We just did energy balances here, and I'm calling this right here, I'm calling that work. And that's the same between the power cycle and the heat pump, and that's what's going to allow us to really do this problem. So at this point, we have this W here, we have the same W here, but this one is related to terms with the power cycle, this one's related to terms with the heat pump. We can now take this equation, and we want to keep it the same, so we got to do something similar to multiplying and dividing by the same thing. But we want to take this Q naught and do some algebra with this stuff over here. And we want this QS to do algebra with this stuff over here. So I'm going to bring this equation down. So we had 1 plus Q naught over QS. And actually, I'm going to just neglect this 1 plus for a second. I'm just solving for this Q naught over QS. I'm going to do a little algebra trick. So I need to multiply and divide by this W, and I need to do it in a way. But I want only one item at the bottom of the fraction. And so what I'm going to do is I'm going to take the reciprocal of this, and I'm going to take I'm going to take this as W over that. This is still a valid algebraic statement. So notice these W's would cancel, this Q naught would come up to the top, and I still have this equality. But now, since I've written it like this, I can take this W, and I'm going to use this for the power cycle on the top. So we have QS minus Q1 over QS, and this is divided by this W for this one is Q2 minus Q naught all over Q naught. And now I can start doing some simplification of this. We now have on the top we have Q naught divided by QS is equal to 1 minus Q1 over QS, and on the bottom we have Q2 divided by Q naught minus 1. Now, this ratio and this ratio both belong to their corresponding different cycles. So Q1 and QS both belong to this power cycle. Q2 and Q naught belong to the heat pump. And now we can use our definition of temperature and we can substitute for those ratios. So we know this is equal to 1 minus T1 is at the dwelling temperature over T source. And then we have T dwelling over T naught minus 1. So this was just this Q naught over QS term, and so if we wanted our total thing, we needed a 1 plus this, we would need a 1 plus here, and we would also need a 1 plus over here. And so we've essentially solved for it. We know that our ratio Q1 plus Q2 over QS is equal to this 1 plus Q naught over QS, and we just showed that it is equal to this statement here, and it is a function of all of your temperatures. I've also saw this from another source, written in a little different form, but this is correct. But we can do some algebra to make it look a little nicer so we don't have all these ones here. We can get rid of all of these ones. So I'm just going to quickly go through, and this is just purely algebra. So let me rewrite this a little bit. So this first step basically took this bottom of the fraction and I made this 1 have this be the top and the bottom, and then I'm adding these two terms on the top here. And so you can see this TD or T naught minus 1 is the same thing here, and now I can simplify the top. You'll see, oh, we have a minus 1 and a plus 1. So those will cancel out. So I'm going to cross those off, and now we have something that looks like this. At this point, I have all these denominators in the fraction. I have two of them are T naughts, one is TS, so I'm actually going to multiply through top and bottom by T naught to get rid of these two, and I'll get this one will have 3 terms, but it'll look a little simpler. Okay, at this point I want to get rid of this, so I'm going to pull out a 1 over TS term from this on the top. So if I pull out the 1 over TS, I get something close to, and we're almost there. So the final form, what I'm going to do is this TS can be imagined as coming down to multiply by this, and then I'm going to pull a common TD factor out of this. And so the last form I want to have is TD over TS, and this is still multiplied by the TS minus T naught, and this bottom is still TD minus T naught. So these two differences based from our lowest temperature, these would both be positive, and we would still all get this. And this is, remember, this is all still equal to the ratio of these heat transfers. This is a little simpler solution, but the one I had at the very beginning is still valid. It's still a function of temperatures. It just doesn't look quite as pretty. So that is the end of this problem. Hope to see you in the next videos.